Did you use the link?
Yeah.
Okay. All right. It actually sounds like you're. Actually, it sounds more like you're God when you come through the big speakers. Right. So the preamble didn't work.
Yeah, here, I'll wait. If I can load, I can make my computer pay attention to me. And do this. And then like it's just like that.
Oh, here. So you're like screen sharing.
Is it working? Yeah.
Yeah.
Is it working?
Nice. Yeah. So I can
So
see.
like there's no next button or anything.
Okay. I think the same thing happened. I think Reed tried it and it didn't work. So what I'm going to do is sort of fix it. There we go. Oh,
Okay.
I'm going to change to me because I'm better looking. Okay, but you actually you seem to have gotten the big idea. The derivative of that is that, and you also notice that x had to be greater than 0.
You're really delayed. On the computer. There's some delay, and I was like, "What are you writing?" You started writing it, but I can hear you.
Oh, really? So my voice.
It's on Safari, so that might be why.
Oh, okay. All right.
Oh no, it caught up. It caught up. Okay.
Hey, I finally caught up. What do you know? So you found that out from the investigation?
Yeah.
Yeah. So that's true. The domain of x is always greater than 0 for any logarithmic function. So you can't have values of x that are less than 0. So that's like a perfect observation. That's great. Am I still delayed?
No, you're good.
Okay. All right. I'm going to do a quick proof of that. Do a quick proof of that. So, really, log is really just the inverse of the exponential function. And when we're doing the inverse, we can actually find the inverse just by exchanging x and y. And graphically, that winds up being the reflection of the curve y equals e to the x in the line y equals x, which we sort of saw in the preamble. It didn't exactly work. Okay, and I'm going to do some magic here. We're going to do this derivative, and it actually involves something known as implicit differentiation, but I don't think you're going to find it too weird. We don't do it normally in this course, but I think this is kind of a fast way to do this proof. So this is really the same as saying that y is equal to the natural log of x. So those two statements are sort of the same. Okay, let's take the derivative of both sides. So what's the derivative of x taken with respect to x? So just like normal.
1.
You are right. And the derivative of e to the exponent y is?
E to the exponent y.
Exactly. Now, the last thing that we have to do is we have to use the chain rule, because y is actually a function of x, and we're taking the derivative with respect to x. And so what's the derivative of y? And
Bring it up front, so it be y e to. Oh, okay.
it's actually y prime, yeah. That's right.
Okay.
So let's isolate y prime. So we're going to divide both sides by e to the exponent y. So y primed is 1 over e to the exponent y. But guess what e to the exponent y is equal to?
X.
Yes! So y prime is 1 over x.
Okay.
Anyway, that's a quick, I don't know if you call it a proof. I guess you call it a proof. You demonstrate, though, that the derivative of y equals e to the exponent x, or sorry, y equals the natural log of x is 1 over x. So that, the fact that that derivative exists actually has all kinds of sort of neat implications. Okay, how are you on remembering all those logarithm rules? Did those seem like kind of come out of left field?
Which one?
Oh, maybe you didn't get to them. All right. Well, we're going to get to them now.
I may have it, just not sure.
Okay. So let's, we're going to do the derivative, and I think we can do this two ways. And so we can actually use the chain rule, but then we can also simplify it using logarithms. So, do you want to take a stab at it? I promise I won't be mean if it's wrong. Don't know what you're doing?
I got confused.
Okay, all right. So the derivative of y equals ln x, the derivative would be 1 over x, right?
Okay.
And so y
So it's just 1 over x cubed?
exactly.
Oh, okay.
And now we're going to do the chain rule, and what's the derivative going to be when we get doing the chain rule? Because we have to do the derivative of this.
Because it'd be an exponential, so it'd be like, are we switching anything yet, or are we just keeping it? We're just keeping it equal to y.
Oh, everything's cool. We're just finishing the chain rule. We've done the derivative
Yeah.
of the outside function. Now we're doing the derivative of the function on the inside, which
Oh, so then it'll just be like 3x to the 2 squared?
is exactly.
Okay, gotcha. Gotcha.
Yeah. I bet you thought that was hard. And so this actually can simplify to 3 over x. And of course, x has to be greater than 0. And the restriction actually comes on up here. Okay. That makes sense, right? Okay. I'm going to show you how to use the laws of logarithms to make it even a little easier. So I don't know, that advanced functions, it was a while ago. But we can actually rewrite this, and we can change where the exponent goes. Do you remember that? Way back?
Yes. I know. Not really.
Where does what can we do with the exponent?
Does it go replace y?
Actually,
The y and the exponent switch, or?
no, actually we can put it down in front of the natural log.
Oh, yes, I kind of remember this now.
Do you remember that? Yeah, okay.
Yeah.
There are a couple of other rules. One of them is the log of a product is the sum of two logs. And the other one's the log of a quotient is the difference of two logs. Anyways, we can actually put the 3 in front.
Okay. Ln's just natural log then?
Yeah, ln just always means log base
Okay.
Euler number. Yeah.
Okay.
I bet you thought that was in all this time on your calculator. The in button.
Oh. Well, that makes sense now.
Yeah. Okay, ready to do this derivative?
Yep. So it'll be just 3 over x, because.
Exactly.
Okay.
Yep. X is greater than zeros because we don't ever have to worry about that. No, we don't ever have to worry about that division by 0 thing.
Yeah.
Okay, perfect. Okay, let's do this one as a chain rule question. Ready to try? Yeah. So what did you get for the derivative of the outside function?
Would this be 1 over 6x to the exponent of 3?
Yes. And now we're going to do the derivative of 6x to the exponent of 5/3.
10x to the exponent.
2/3.
Yeah.
Yeah. Perfect.
Yeah.
And so we can do a little bit of simplifying. So we can divide that by 2 and divide that by 2. So 5 over 3. And we can reduce the x on the bottom, right? So we can do some common factoring here. We can divide the top and bottom by 2/3. And this whole thing becomes x to the exponent 2/3. And this just becomes x. So it becomes 5 over 3x.
Okay.
That's easy, right?
Yeah.
One last example. And this one's going to be a review of a log law. This is the natural log of x plus 3 over x cubed. Ooh, ugliness. Okay. Now, do you remember when we had the log of a quotient? We can actually write it as the difference of two logs.
A minus b.
Exactly.
Right?
Hey, that's good.
I think I did do that.
Oh, okay, in the preamble.
Yeah, the preamble.
Nice. And then we can rewrite this one too. The natural log of x cubed. How can we rewrite that?
Natural log, or 3 natural log of x.
Exactly. Hey, I hear family.
Yes, I have family. This is just the weirdest conversation. They're lovely when they're alive. I think the time for flowers, but we can't be fair.
Well, that's good. Okay. So, oh yeah, you can do this one. This one's easy.
Is it just 1 over x minus 3 over x? Oh, x plus 3. Got that 3.
Yeah, that's right. Because it's because this is the inside function, it just stays the same. Yeah.
Yeah.
Yeah, perfect. Okay, now there is actual trickiness with this argument to the log, because everything is fine as long as this whole argument is positive.
Mm-hmm.
So we almost have to think about this in terms of an interval table. Okay. Because it's going to change signs when x is -3, and it's going to change signs again and when x becomes 0. So we have the interval from -infinity to 3, and then we have, -3. Then we have the interval from -3 to 0, and then we're anywhere where x is greater than 0. So in this interval, x plus 3 is
Negative.
and x cubed is,
Negative.
yeah. And so the whole argument, x plus 3 over x cubed, is going to be positive. And so we can actually have x values that go from -3 on to -infinity. So this function exists when x is less than -3. However, when x is between -3 and 0, this is
Positive.
and this is negative.
Negative, yeah.
And then the whole thing is negative. And so actually this function is not going to exist when x is between -3 and 0.
Mm-hmm.
And then the whole thing is positive beyond there. So as long as x is greater than 0, it also exists. So x has to be less than -3 or x has to be greater than 0. And this is our derivative. That's it. That's easy. Hey, could you see the bridge of death?
I was tempted to watch it, and I was like, no, I said I did quickly.
Oh, okay, all right. It was only 3 minutes. Gee.
I wanted to. Yeah, but when I started, we were already video conferencing.
So I guess that's it. I'll post some exercises and believe it or not, we've got like 2 or 3 more lessons, and then we're done the calculus part of the course.
Okay.
All right. That's good. Okay. See you. Oh, come on, think
We're talking
about it.
about science fair.
Yeah. Here, I'll